Hello, everyone. My name is Connor Walsh, as was just mentioned. I'm a faculty member at Harvard. I direct the Harvard Biodesign Lab. It's pretty exciting for me to be here today as part of the Jaguar Land Rover Tech Fest. We recently, about a month or two ago, so not that long ago, started a collaboration with Jaguar Land Rover and also with Tata in the area of wearable robots. So that project has just started, so I can't really speak too much to that project today, but I'll talk about some other work that we're doing and hopefully give you guys an idea what the answer to this daunting question is, can technology save humankind? I think it's a really good question. So to get started, just kind of to think about, technology, I think about robotics when I think about technology. I'm a roboticist. That's what gets me really excited. And I think oftentimes we're made to think that or have a very dystopian view of what robotics could mean for us and what it can mean for society. And I think in particular, Hollywood often convinces us that, robots are going to come, they're going to become really advanced, and they might even turn on us or make us obsolete. So I think that's kind of maybe a negative way of looking at things, but I think today I'm going to try and look at things from a more positive point of view. And really think about, should we be thinking about humans versus robots, or in competition with robots, or should we be thinking about it more as a collaboration between robots and humans? So that's really the way I like to think about it. That's really kind of the type of work that we do in my research group and a lot of what we focus on at Harvard. And I think I'll get started today by just going through a few general examples that aren't our work, but I think for me are pretty inspiring to think about what actually it can be enabled by technology and what can actually be enabled by robotics for society. So the first thing is really thinking about safety. So this here is a picture of inside Fukushima after the nuclear disaster that happened a few years ago. You can see a robot here in the middle, and this robot is basically going somewhere that would be unsafe for humans to go in order to be able to kind of survey the damage and look for people who might still be inside. So that's really, I think, an excellent example of where robots really can provide benefits for society in doing things that would not be safe for somebody to do themselves. Another area, I think, is in the area of efficiency. This is one of my favorite images. It's a image of an industrial setting and a factory floor. And I think robotics really kind of got going or started in the 1980s. So it's actually not that long ago. But really, that's where a lot of the core technologies for these types of traditional types of robot manipulators and systems really got developed. I don't think this picture does it justice. I think you really have to see these live or see a video to see kind of the coordination of all of these different machines and how it basically enables things to be done much more efficiently than you would be able to without the use of technology. The other area that I think is also important for society is the area of exploration. So I think here is an example of a rover on Mars. This has gone somewhere where humans cannot go right now. And I think space exploration is one of the great examples of where robotics really enables us as a race to be able to kind of think about beyond our own planet and think about exploring even further. I think it's clear from this image that we have a lot of common with robots as well. Clearly, robots like taking selfies as much as we do. This is a robot selfie from space. But these three areas, basically safety, efficiency, and exploration, I think are really kind of three kind of big general areas that robots can have really great benefit for society. Now, one thing that you may have picked up on, I'll ask a question to the audience. What did you not see in any of these last three pictures? Humans, right? You see robots, but you don't see any humans. And I think traditionally, especially in factory settings, space is an obvious example, but robots have really been developed in a way where they're kind of operating separately or in isolation from humans. They haven't really been operating close with humans. Does anybody have an idea of the probably best example of a robot that's operating closely with humans? Car, yeah, so we're getting towards robotic cars. I think the first really one is a robotic vacuum cleaner. So, Roomba from iRobot, I think this is really the first commercial example of a robot that is not isolated from humans, but is actually working very closely with humans. And you can see that this cat in particular has figured out, really well how to basically kind of cooperate with that robot for benefit to be able to kind of use it as a staging kind of platform for attacking this dog. But with a little bit more seriousness, I think from a robotics research field or robotics research community, if you go to any conferences today, one of the big teams and one of the big areas that's getting funded is really trying to think about developing robots that are operating very closely, in close proximity, and in cooperation with people. And that's kind of a change in the way that the robotics research community has been thinking about different types of robotic systems. So that's one of the areas that we really focus on at Harvard. At Harvard, we have a growing robotics program. I think you can look at it across the world, and I think robotics as an academic field is really growing quite rapidly. So we have a growing robotics program that really is focused on this idea of how do we have robots and technology that can really benefit society. So about 6 years ago, I started the Harvard Biodesign Lab. So this is a research group that's really focused on developing technologies for augmenting healthy people, the performance of healthy people. So if someone is carrying a heavy load or lifting a heavy load, how do we develop wearable technology that can enable them to do their job safer and more efficiently? And we also then kind of do a lot of work with patients and medical applications where we're trying to restore function or restore mobility for people who have some kind of physical impairment. And I'll talk most about the medical applications here today. So apart from our great team that we have of engineers, designers, biomechanists, clinicians, we have patients who volunteer with us who are really great members of our team as well. And this is Kelly. Kelly suffered a stroke, so she's walking outside of the lab here at Harvard. She comes in quite a lot. But, you know,
brain, half of me doesn't exist. It affects pretty much everything. Every single day, it's where can I go, and when I get there, how much can I participate?
So she's just an example of one person who suffered a neurological injury or another type of injury that's left her with an impairment that means she doesn't have the same level of performance that a normal, healthy person would have. And so for someone like Kelly, when you suffer a stroke, basically what you undergo is some type of rehabilitation or physical therapy. This is just an example of that here. You know, this video is from a few years ago, but this would be pretty typical of the types of therapy that people get after they suffer a stroke or other neurological injury. You can see one thing that really pops out from this is how labor intensive it is. You know, you're really trying to get someone moving again and get someone going. Because of that, it's really restricted to clinics. People have to come into a clinic or a hospital setting. They have to travel there. Insurance companies often don't reimburse this or fund this for people for more than 10 weeks. So, you know, they're not really getting enough therapy. And the sad thing is that most people who have this type of injury, you know, while they might get a little bit better, they still don't really get to the level that they can operate successfully around their community. So that's kind of one of the big things that we focus on in the lab. But if we think about solutions and you look to Hollywood, there must be solutions that exist, right? We must be able to do something better. So I'm sure a lot of you have seen this movie Iron Man. It's kind of the vision that Hollywood gives us for wearable robots, that, you know, they can give people superhuman strength and power. So, you know, he's able to kind of kick this car kind of out of the way very effortlessly, and also able to fly and do lots of other things. And so I think sometimes when people think about wearable robots or exoskeletons, they have this view of these kind of more impractical systems that are more fantasy than actually reality. And I think one of the big things is that inside here, you know, the kind of thing that's often glossed over is that you have a miniature nuclear reactor that is powering this suit, right? So that's not practical. We don't have that today. We can't use that technology. So we have to think about what are alternative approaches for these types of systems that are really practical and can provide benefit to people today. So a more sobering video, this is from about 10 years ago. This is me when I was a graduate student at MIT. We were working on leg exoskeletons using more traditional rigid types of components and rigid types of robotic mechanisms. You can see I don't look particularly happy in this video. I look a little bit sad. But basically what we were trying to develop is a robotic system that will be able to help me carry load, or help a person carry load more efficiently when walking it, so that these legs would do the work so that you didn't feel it. And one thing that I think is pretty obvious if you're looking at the video is, apart from not looking happy, it changes the way that you walk. So the added kinematic restrictions of the mechanism basically kind of modify your gait and allow you not to walk in the way that you would normally want to. And so it kind of forces you or restricts you to a certain type of pattern. And whenever you do that for a person, it's really not ideal from a biomechanics or a movement kind of point of view. So since that we were one of the early groups to be working on these types of exoskeletons, a lot of great work has been done actually on exoskeletons for people who are fully paralyzed. So that top video is an FDA-approved exoskeleton. The person who's walking it has no movement from the waist down. I believe she's actually walked a full marathon in this device, over many days. But it's really amazing to think about how far the technology has come that a person who's fully paralyzed can get up and walk with technology like this. However, like Kelly, there's a lot of people out there who can walk, but just not very well. And so they don't really need, or they wouldn't really benefit from a traditional rigid type of exoskeleton or robotic system. All they really need is a little bit of a boost that would help them be able to walk a little bit more efficiently. So if you look at the landscape for these types of assistive devices, you have these cool new systems here, these exoskeletons that are giving active assistance, so actively helping people when they move. And then, back here, you've got technology that really hasn't changed for over 100 years, these canes and walkers, and there's really nothing in the middle. So what we're really focused on is, can we develop systems that can give active assistance, but are really not restrictive, are really lightweight, are the types of devices you can wear all day, every day. That's what we're focused on and been working on over the last 5 years or so. And so when we started working on this, we wanted to try and do something a little bit different. So the big challenge in the previous rigid exoskeleton that I showed is basically that rigid exoskeletons have weight and they impose restrictions on a person. So when we think about clothing, we're all wearing some form of clothing today. It's really made with textiles. And so we started to think about, can we really leverage textiles a lot more in the construction and design of wearable robotic systems? So why textiles? So I think they're inherently compliant and flexible and lightweight. That's one thing. They actually, from a strength to weight ratio, are much better in performance than steel. So you can use textiles to really support very heavy loads, and they can be really quite strong if you use them in the correct way. You can get them in many different types of properties. So textiles, you've got this whole array of materials to choose from. And then it's pretty easy to manufacture these using kind of techniques that are very readily adaptable to mass manufacture and affordable manufacture for these types of devices. So we're a robotics research group. I'm a mechanical engineer. We have 6 sewing machines now in our research group. That's not something that we would have expected when we started 5 years ago, but that's really how our work has been evolving, really trying to bring this textile and apparel design expertise alongside the engineering and the robotics expertise as well. This is our studio that we've set up. We call it the Byron-inspired Apparel Design and Sewing Studio. I don't know if you get that acronym. You have to be a badass to be able to get trained in there. So that's really been a major focus of our work. And I'm going to just talk a little bit about 2 kind of projects, one for the lower extremity, so helping with walking, and another project for the upper extremity, where we've been applying this new approach to wearable robotics and textile-based wearable robotics to help people with physical impairments. So the first is what we call an exosuit for patients post-stroke. This is what the device looks like here. So you're basically wearing the motors, the batteries, and the electronics, so those heavier components are only worn around the waist of a person. They're not worn kind of on the legs. And then we're using textiles to anchor and attach to the body without the use of rigid elements. And then cables to transmit power and signal from this unit up here, this actuation unit we call it, down to the ankle joint. And in this case, we're targeting the ankle joint for patients post-stroke. This is usually the place of most severe impairment for these people. So that's really where we decided to focus our efforts. So the way that the device works is really quite simple. And we have a lot of people that wear spandex in our lab. But basically, what we're doing is trying to understand what are the muscles doing during normal walking, and can we give a little bit of a boost with the robotic assistance at the same time that those muscles are trying to fire. And so that last animation kind of showed muscles turning on and off. So there's this synchronization between your brain and your muscles during walking that happens automatically for most of us. But for a patient, we're trying to figure out how to help them learn how to do that better themselves. And you can kind of get an idea here of these cables. They're basically pulling across the joint, so they're what's giving a little bit of a boost and helping to lift the foot every step that a person is taking. And you can kind of think a little bit, an analogy is a little bit like a swing. So if someone's moving back and forth on a swing, that's a very dynamic system. If you just give a tap at the right time, you can really keep that swing moving forward. And we're basically trying to do the same thing with walking, is give that little bit of boost of energy at the right time and be able to help people walk more efficiently and more naturally. And so I think one thing that's also obvious from these videos is that the system really doesn't change how a person walks. Compared to the video of me walking with the rigid exoskeleton, these devices really allow you to walk very, very naturally. So this is just an image that kind of shows that prototype again. You can see that it's very modular as a platform. It's very customizable. And we've started here targeting the ankle joint of the paretic leg, so the more impaired leg for a stroke patient, which is a very, very common presentation. The heavier components are mounted up here, but you can imagine that it's very easy to make this system work for both legs or the hip joint. So it's really a platform technology that you can apply to many different areas. This video here, the near leg of this participant is the more affected leg. So you can see now they're basically not pushing off very hard. But then when we add the assistance with the exosuit, it really gives them a significant extra boost that allows them to walk more symmetrically. Their foot is clearing the ground better. They're propelling themselves forward better as they're walking. And this is Kelly again, kind of in our lab on the treadmill. So in addition to building these systems, one of the things that we try and do is understand when we put a system like this on a person, how do they adapt? How do they respond? And when we try and quantify that and use that information to guide the ongoing design of these systems. And we do that in close collaboration with our clinical partners. So Lou, who you see in the video, is a physical therapist who's a faculty member at Boston University. So it's really this kind of mix between engineering and medicine, trying to understand how do we kind of make a difference for these people. Just as a quick kind of side-by-side, you can see here on the left, the participant walking with no assistance from the device, and on the right, walking with assistance. And just as it's a one case study, but I think it gives you an idea, and we've shown this with larger studies, that the system is able to give a person that extra bit of a boost to allow them to walk faster, more symmetrically, more economically. And the reason this is important is for a lot of these patients, because they have this impairment, they're basically restricted to the home. They can't walk very far. If they don't walk far, that has negative health benefits. So trying to keep people mobile for longer, allowing them to kind of have the ability to integrate into their communities, to go to the local store, that's something that we think these types of technologies will enable. So moving forward on this project, so for this project, we've been working on it for about 3 years, and we've partnered with a company called Robotics. They licensed the technology from Harvard. Their engineering team is currently creating a prototype of this system that will be kind of starting a clinical trial next year in 2018, and we hope that it'll be available for use in clinics, where it could be used in these types of scenarios where you'd have a physical therapist basically putting this system on a person, and instead of having 3 people trying to move the legs, the therapist would be able to think about the more high-level aspects of the person's therapy, and the device would be able to provide enough assistance and coaching to help the person be able to move and walk around. So that's kind of one of the devices that we've been focused on. So the other area that we're focused on is the upper extremity, so moving up the body to the arm. There's a lot of people, such as spinal cord injury patients, people who have ALS, muscular dystrophy, and they really kind of have lost the ability to perform activities of daily living. So everyday common tasks that we all take for granted, such as eating and cleaning, and, interacting with others, going shopping. So we're starting to try, and this is a little bit earlier stage, but we're trying to think about, can we really create a fully soft textile-based wearable robot for the arm that would enable someone who's lost function of their arm be able to actually move their arm around and be much more independent. And the way that we're thinking about this is, you saw in the previous design, we still had some cables, some rigid elements. We're really trying to think about the part that's on the arm. Can we really just make this out of only textiles, only apparel? So when you're wearing it, it really just feels like a piece of clothing, but then when you power it, you can get assistance from it. And the way that we're thinking about that from an actuation point of view, or a force application point of view, is basically through air. So this here is a balloon, and if you have this balloon inside a textile sleeve, basically that's the mechanism that we're using when you inflate that balloon to generate forces and generate interesting types of motions. And this is kind of an example of some kind of the emerging work in the field of soft robotics. That's another area that's really taking off quite a lot at the moment as well. So depending on the type of textile that you used and the material properties of that textile, you can get all these cool, interesting types of motion. So you can have actuators go from short to long, you can have them bend, you can have them twist, and all of this is basically programmed into the material when you choose the textile and its specific material properties. So I'll show a few examples of some cool motions that you can achieve. So you can see here, this is just a textile. You can wrinkle it up. It has no real resistance. And this has 2 balloons inside it, so you can actuate it in 2 different ways. One is when you inflate the first balloon, you can stiffen like a beam, so it can become very strong and stiff and straight. And then when you inflate the other balloon, you can get that interesting shape that mimics kind of the knuckles of a finger as a hand would be closing as well. And so this kind of ability to go from very, very flexible, roll it up, crumple it up, provides no resistance, to then when you pressurize it, and to be able to kind of like generate different types of motions or different types of shapes, I think is really exciting from a potential for a wearable robotic point of view. Another thing that you're able to do with these types of devices is program to have certain end motions. So later on, I'll present a device for the shoulder where you'll see that that's beneficial. But you can basically have them go to 180 degrees or 360 degrees, and you select this. As a designer, you have the ability to actually choose how do you use the geometry and the material properties to get the shapes and motions that you want with these systems. The other thing that we've shown as well is that you can actually, by understanding the motions that you want to assist, so let's say we want to assist the thumb motion with a glove, you can actually choose the material properties of that actuator to kind of mimic the motion of a thumb. So the reason this is important is it allows you to have a system that could be very, very simple, very, very affordable, very, very accessible for people. So here, all we're doing to generate this complicated thumb-like motion is pressurizing that actuator that is essentially just a balloon. So that's kind of really exciting to think about how you then adapt this to wearable applications. So one of the wearable applications that we've started prototyping is a soft robotic glove. You can kind of see that here, just lifting up this plastic strawberry. But the idea is, can we actually start integrating these actuators into a wearable device that a person would really be able to wear throughout the day when they're at home? And you can see that when the actuators are pressurized, you can see that they inflate, so they don't restrict opening of the hand. And then as soon as they're pressurized, they basically help that person grasp that object. And the reason this is important is that there's a lot of people out there, similar to walking, that they have some residual ability in their hand. They have a little bit of movement, but they just don't have enough to be able to kind of be independent. So we're not trying to kind of provide 100% assistance with these types of devices. We're just trying to give a little bit of a boost to enable them to be able to have the function that would make a difference. We also the vision for these is really that you put these on like clothing. We're not quite there yet, but that's really where we're trying to go, is that you have these devices, and whether you put it on yourself or you have a caregiver put it on, you can really put these devices on like a piece of clothing. This device here is helping the shoulder, and so you can see that here, this is an actuator that's bending to 180 degrees underneath the shoulder that's basically helping that person lift the arm. And the reason that we're focused on the full arm is that depending on the pathology, some people might have more impairment at their hand, or some people might have more impairment more proximally, so closer to their shoulder joint as well. And so you can see here how by combining different actuators, we can really kind of achieve many different types of motions that would be very, very hard to do with a rigid, traditional type of robot or exoskeleton. And the vision really for both the lower extremity and for the upper extremity is that these devices could eventually be worn underneath clothing. So people won't even know that you're wearing a wearable robot and may not really even be aware that you have some type of disability for some applications. So, another aspect of these devices that will be important from a control system point of view, so how does the device know what you're trying to do and how does it automatically help you, is embedding sensors in these devices as well. And we would love those sensors to also be based on textiles. So this here is an example of a conductive textile material using silver, that basically if you integrate this into this glove, you can see that you're able to kind of monitor the movement of a person's hand using these textile sensors. So there's still a long way to go here to make this truly integrated with all the wiring and the connectors and everything else. But we really want to work towards a device that you can put in the washing machine, clean it, take it out, put it on, plug it into your power supply, and all of a sudden you're wearing a wearable robot that provides you assistance. So this here is just a short video example. This work is still pretty early, work in progress. This is Charlie. He's one of our participants as well that volunteers his time. But you can see here that he wasn't able to lift that cup himself or that can, but using an early prototype of the glove is able to do that, lift that object, and would be able to have a drink himself in a way that he just wouldn't be able to otherwise. So they're just examples of two projects, both for the lower extremity and the upper extremity, that I think kind of show the potential for technology to really kind of have a significant benefit for humankind. And so to think about, it's still research, it's still in an academic environment, it's not yet in the real world, but we're trying to move it in that direction. And when you think about where have we come with exoskeletons, so people have been thinking about wearable robots for over 100 years, and had some crazy ideas from the 1800s. General Electric had a system in the 1960s, but you're seeing this gradual progression of systems that are becoming more and more practical. And this is more from a research point of view that I'm kind of showing here. But I think what's really exciting for me as a person working in this field is that over the last 10 years, you've seen this explosion, and this list doesn't really capture it at all, of all the different companies that are now really getting significantly involved in the field of wearable robotics. Some of these are startup companies. Rewalk is a company that we've partnered with. This is their rigid exoskeleton, and they're taking our Exosuit to market as their next product. Exobionics is another startup. But some of these are also big companies like Panasonic. Honda have been working on this for about 10 years, different types of rigid exoskeletons. So I think it's a really exciting time for the field to think about where can we actually go with this types of technology, whether it's rigid or whether it's soft. I just think there's a lot of potential to really improve the lives of people pretty significantly. And so when we think about, where will we be in 10 years or 20 years, I think if we look back and think about some other types of technologies and think about how they've moved along. So basically, the first mobile phone was in 1973. And I think no one would have predicted where we are today and the capabilities that we have with cell phones today. Well, maybe some people like AT&T would have. But I think the majority of us, really wouldn't have imagined that things would have moved or progressed so quickly. So I think when we think about wearable robots, I think we can also think about where, how are we going to see technology scale? How are we going to see them become optimized? And how are we going to see them kind of be deployed in our everyday lives? And then I think the last area that's also maybe relevant to the automotive industry is when you think about driverless cars. This is from the DARPA Urban Challenge, so another academic research program. You can hear the siren because people have to be very careful around self-driving cars. So this is an example of that urban challenge where they had different academic groups or companies participate in a competition to try and drive around some course. And this was in 2007, so about 10 years ago. You can see here all the technology that's on top of the car. It's not integrated. You're probably like, that's not practical. And I would say when I was a graduate student at MIT around this time, I had some colleagues, students who were working in this field, and I was like, that's just never going to happen. We're never going to have driverless cars. But I think it's really just amazing to see how quickly the technology has come. So in this case here, you're watching this car. I think in the moment it has a little bit of a hiccup where it kind of gets a little bit confused. But to go from prototypes that look like this, where we're seeing a car that is still a prototype developed by researchers. But I think it's amazing then that once society kind of gets behind that idea and says, yes, this is important, yes, this is possible, yes, this can provide benefit, I think it's really exciting to see kind of how far it has come in the last 10 years. And I think just this little blip at the end, in their driving, which, I think is really a small kind of a deviation from what's a really impressive experiment, really highlights kind of going back to those two areas of safety and efficiency. So, I think if all cars were driverless cars, I think statistically things would be safer, assuming that you get the technology right. And I think that's ultimately the way it's going to go. And I wouldn't have thought that 10 years ago. And I think from an efficiency point of view, I don't know how many of you like being stuck in traffic and moving around, but imagine if all of a sudden you no longer have to waste time in traffic. For society, we get that added benefit of being able to do whatever else we need while we're driving, while we're in our car. So I think that's kind of those two areas for technology and robotics. I think safety, efficiency, and also going back to that third one, exploration. I think that's really why technology has the potential to save humankind and at least enable us to go further than we would be able to without it. So with that, I'll end. I'm happy to take questions afterwards, and thanks a lot for allowing me to participate in this exciting event.